Hi, welcome to the tutorial on model evaluation metrics. By the end of this topic, you will be able to define and calculate error corresponding to the mean regression model, evaluate the regression model's performance using different metrics such as mean absolute error, mean square error, root mean square error. So far, we have just been visualizing our models and their predictions and using those to comment on the performance of our models, that is, goodness of their predictions. But as data scientists, we often want quantifiable results in the form of numbers. Hence, we will now look at different quantifiable metrics such as mean absolute error, mean square error, and root mean square error, which will help us infer how good or bad our model's predictions are, as well as compare one model with the other. Let's start with mean absolute error, or MAE. So, when we plotted the residual plot, we looked at the difference between the predicted value and the actual value for each data point. This difference, that is the residual, is also called the individual error term. And if we want to find the overall error of the model, we can simply add all these errors and take an advantage of that, right? So let's do that for our first model, and let's call that mean error. Here, we simply calculate the sum of the residuals for model 1 and divide it by the number of examples. In the next line, we simply print the cost with rounding off to the 7 decimal places. Now wait a second. We have got mean error as 0, which means our model has 0 error and is perfect. Why is that happening when we know our model is not perfect and predictions are not the same as actuals? Can you guess why we are getting our mean error as 0? Yes, that is because some of our errors are positive meaning. In some cases, prediction is more than the actual, and some of our errors are negative meaning. In some cases, prediction is less than the actual. And when you simply add these up, they cancel out each other and lead to mean error being 0, which is a misleading output. To correct for this, we use something called mean absolute error, or MAE. So let's discuss MAE now. In this, as the name suggests, we first take the absolute value of each individual error term, sum it up for all the data points, and then take a mean. So let's do that now. Consider y hat be the predicted values, y be the actual values, n be the total number of data points, and you know that the residual or individual error term is given as y hat minus y. So let's sum over absolute value of all of them and divide it by the number of total points to get mean absolute error. Let's try this in Python and find out whether we will get mean absolute error as 0 and whether the mean regression model based on the overall grade was actually better. We will first define all the variables to calculate the error. Y will be our sale price, y hat 1 will be the mean sales, y hat 2 is the grade mean, and n will be equal to the number of points. And on checking the length of these, they all come out to be equal, which means we are all set to calculate the error. Let's first calculate the MAE corresponding to model 1. Note that I am using the absolute function because we do not want the positive and negative values to cancel out each other. We can see the error comes out to be 199168, which is not 0. Great, right? Now let's calculate the error associated with second regression model. This comes out to be 137081, which is lower than the error corresponding to model 1, and this confirms what we inferred visually earlier, that is, model 2 is better than model 1. The good thing is, we can calculate the same thing using the scikit-learn library so that we do not have to calculate the error ourselves every time. Let's see how do we do it in Python. Quite easy, right? Okay, we are getting a few numbers as MAE, but what these numbers actually say. This mean absolute error tells us how far, on an average, the actual point is expected to lie from the predicted point, which tells us how good or bad our model is. Let's look at the next valuation metric, that is mean squared error, or MSE. The formulation of the mean squared error is quite similar to the mean absolute error, except it has a square term added to it. As the name suggests, we first square the individual errors, sum them up, and then take a mean of it. Now you might ask, how is this different or useful than the mean absolute error? If you notice, the mean squared error, that is MSE, computes the square of the difference between the actual and the predicted points, which has a twofold effect. It turns all the differences between the actual and the predicted into a positive quantity. Furthermore, it incurs extra penalty for the larger difference between the actual and the predicted values. Therefore, the error of the model explodes for the large difference between the actual and the predicted values when measured as MSE. Let's see how we can calculate the MSE in Python using the scikit-learn library. For that, we start by importing the mean squared error function from the sklearn.metrics module. After this, I am simply calculating the MSE corresponding to both the models. We can clearly see that the MSE value corresponding to model 1 is significantly larger than model 2. Now we will move on to the next metric, that is RMSE. Although MSE does tell us about the presence or absence of the large errors in the model, but it fails to give the expected average distance between the actual points and the predictions, as we saw in mean absolute error. To find a middle ground between the interpretation of distance of the actual point with respect to the predicted point and penalizing the larger errors, we will now look at the root mean square error, or the RMSE. The formula for RMSE is as shown on the screen. In RMSE, we are essentially calculating the mean square error and taking the square root of it. As a result, the large errors are being penalized, yet the scale of the error is closer to that of mean absolute error. Unfortunately, root mean squared error is not available in scikit-learn, so we will improvise. We will simply calculate the mean square error and calculate the square root of the resultant value. You can clearly see that the root mean square error is higher when compared to the mean absolute error, but it is still in the similar overall range as mean absolute error. So that's it in this tutorial. In the next tutorial, we will discuss 2 more model evaluation metrics. See you then.